Alright, we are now going to discuss the potential energy of a mass spring system. So here the system is that you have a mass of some value attached to a spring, and from our previous discussion we know that we can select any point we like to have potential 0, and it turns out that in the mass spring system it's only natural to set the potential to be 0 at the equilibrium position. In other words, when this mass is at x equal to 0, at this position we would say that u at x equal to 0 equal to 0. Okay, we shall then show that if we set this reference potential to be 0 at the equilibrium, the potential energy is given by this very familiar u equal to half kx square. In other words, if there is a displacement of x from this equilibrium position, the potential energy stored in the spring is given by half k a square. If it's compressed so that x equal to minus b, then the potential energy is half kb square. Notice that by this form, and this form is of course dependent on this choice of reference potential, but anyway, in this form we see that the potential energy is always positive, so that's an interesting thing to remember. It is of course just a choice we make, but it's a useful one. So the derivation is in the following way. Let's find the work done by the spring force in going from x equal to 0 to x equal to a. So we have the work done in going from 0 to a is just, you have an integration from x equal to 0 to a. So let's pick an arbitrary point x instead of a, so that you have an integration from 0 to x, and this integration just gives you minus half kx square. And the minus of course makes sense because the force acts in the opposite direction of displacement. Anyway, as we discussed, the work done for a conservative force can be defined as the negative change in potential energy. So the potential energy changes from this ux, whatever the potential is at this point, potential energy, minus u0. And then we define this u0 to be 0. We set our reference potential, because you can add and subtract constants to potentials, and you can use that to set the reference potential to be 0. So that now we have the work done in going from x equal to 0 to this some arbitrary point x is minus half kx square, which is equal to minus ux, so that ux equal to half kx square. This very familiar formula. So what's so nice about this potential energy is that we have, for conservative forces, something called the conservation of mechanical energy. So notice the forces acting on this system. At any given time, this mass is sliding on the x-axis, it's going back and forth because of this spring. The forces are simply the force due to the spring, the normal force, and the weight. But the only force doing work here is the force due to the spring, because these other two forces are perpendicular to the direction of motion. Here the object is moving in this direction, and so these are perpendicular. So only this F spring does some work, and this F spring, as we very well know, is a conservative force. In other words, the work done in going from A to B, the net work done, is just the work due to the spring. These other two do no work. Now, if work done is the work done due to the spring only, we have from the kinetic energy theorem, the net work done is the change in kinetic energy. But we also had that this work done due to the spring, being the work done due to a conservative force, can be written up as the negative change in potential, which is minus ub plus ua, because this force due to the spring is conservative. So let's add this all up. We have the work done due to AB was del Ke, but the work done due to AB was equal to only the work done due to the spring, which was the negative of potential. So we have half mvb square minus half mva square change in kinetic energy equal to the negative of the change in potential energy. Let's rearrange this a bit, and you immediately get half mvb square plus ub equal to half mva square plus ua. But you can interpret this in a very nice way. This looks like kinetic energy plus potential energy. We can call this the total mechanical energy when this body is at point B. And similarly, we can interpret this as the total mechanical energy at point A. See, half mva square is kinetic energy at point A, and ua is potential energy at point A. So I hope this minus sign is making a bit more sense now. We defined this thing, right? We set up the work done due to the spring being a conservative force, and we said that it's defined as the negative in the change in potential. So this definition is well done because this sets you up to have a nice form for the total energy of the system. Now if you plug in this ux equal to half kx squared that we found, you just have this familiar expression, half mvb square plus half kx square equal to half mva square plus half kxa square. In other words, you can think of it like this: the potential energy keeps getting converted to kinetic energy and vice versa. In other words, okay, think about it like this: as this mass keeps going from A to B, it's going to keep slowing down, right? It's going to keep slowing down, and the potential energy is going to increase because this is going to increase, but in such a way that this stays constant. In other words, you have this half mv square plus half kx square is equal to constant. You can draw graphs like this which make it easy to understand. You have this graph of potential energy. As x keeps increasing from x equal to 0, the potential energy keeps increasing, and at the same time the kinetic energy keeps decreasing, but in such a way that, for example, at point x equal to 0, let's say you have 0 potential energy and a very high kinetic energy, but their sum is equal to E, and then as the body keeps going in the positive x-axis direction, the potential energy keeps increasing, but of course the body keeps slowing down, so kinetic energy keeps decreasing. But at any point, the sum of kinetic and potential energy is some constant, which is the constant energy E of the system. So I hope at this point the reason why we call these forces conservative is clear. These conservative forces, when they act on a body, when only conservative forces act on a body, you can define some mechanical energy of the system which stays constant while this body moves with time, right? And a spring system is a perfect way of looking at this. So in a spring system, you have conversions from kinetic energy to potential energy. The highest potential energy, of course, is when it's reached this maximum displacement. At this point it stops, and that's this point, right? You have a maximum kinetic, you have a maximum potential energy and 0 kinetic energy, and then it just moves backwards. The total energy remains the same, but of course potential energy keeps changing, and correspondingly so does kinetic energy.